Let's talk about a generative view of clustering. So far, we've talked about two versions of clustering algorithms: hard clustering, where clusters do not overlap, a data point either belongs to one cluster or not, and also soft clustering, where clusters may overlap and a data point may simultaneously belong to multiple clusters with varying degrees of belief. Next up, we're going to talk about mixture models, which are a probabilistically grounded way, a generative approach, doing soft clustering. And what we mean by this is that now every one of our clusters is going to be represented as a distribution, and we're going to try to learn the parameters of those distributions via a generative approach to then understand which one of my points are assigned to which cluster. The algorithm to do that is expectation maximization, and we're not going to have time to go through the EM algorithm itself, but that's, again, yet another iterative algorithm that does these assignments and updates for us in a probabilistically grounded way. So let's first build up our intuition. This was what we saw for hard or soft clustering, right? We started off at the top corner there, two initialized points, the red and the blue cross. Then we iteratively went through the assignment and update steps, and finally, once things started to converge and not change anymore, then we stopped the algorithm. Now, the generative approach to this looks as follows. Start off with the same points, and we start off with the parameters of two, in this case, Gaussian distributions, the mean and the covariance matrix of a Gaussian distribution. And then we said, which one of these points is assigned to which Gaussian? So you'll see here, if I zoom in a bit, that there's a boundary in which it's not so clear whether it's a red point or a blue point. So it seems as if there's partial assignment to each of these distributions. It's as if we're measuring the posterior of every point given, the class conditional of every point given the parameters of the underlying Gaussian. This is exactly what we talked about yesterday in the naive Bayes class, right? We said we're going to be learning class conditionals and then updating the posterior. So this is what we're doing. We're assigning every point to the two Gaussians based on the parameters that they have. And then based on those assignments, what do I do in the next step? I update those parameters. So now you can see that my distributions have somehow been updated. And once again, based on those updated distributions, I go through the next steps, and then finally I arrive at a point where now, if the parameters don't change too much, then I stop. Similar to before, there's a convergence criteria. Yes? I see a couple frowning faces, so all good? Excellent. So let's talk about mixture models in 1D. Suppose we have the following observations as before, x1 to xn. Suppose we know the data is of two clusters. If we happen to know the assignments of points to clusters, as you can see, 5 of the points are in blue and 5 of them are in yellow. If we happen to know this assignment in advance, then we could use that information to estimate the unknown mu and sigma squared of each of those clusters. How did we do this yesterday? We said there turns out to be closed form expressions, the maximum likelihood estimates for the mean and the variance of a Gaussian distribution. And we had this complicated looking expression, but really it's just a bunch of indicators saying, does the point belong to cluster K? If so, then take the empirical mean as the estimate, the maximum likelihood estimate, and take the empirical variance as the estimate, the maximum likely estimate of the variance. Right? All straightforward stuff from what we've done last lecture. So based on the 5 blue points that I have here, I can estimate the mean of the best fitting Gaussian as that point and the variance as the variance of that Gaussian. Similarly for the yellow class. Now this assumed that we knew which one of the points were assigned to which cluster. So what if we don't know the sources? What if we don't have the assignment labels? This is now a bit more tricky because we have to make additional assumptions. We can assume, we suspect that data can come from K different classes, but we don't know which. Now, the complement of this is to say, if we happen to know the parameters of these two Gaussians, so I know this is mu1 and sigma 1 squared, and I know this is mu2 and sigma 2 squared, then we could infer which points likely came from which Gaussian, right? Like this point in the far left is most likely a yellow point, and this point on the far right is most likely a blue point. But then these points here are probably a mix of both somehow. How did we determine these values? We said we're going to write down the class conditional of every point x conditioned on the particular choice of sigma and mu that exists. This was called the class conditional, and this was called the posterior. Okay, so on the previous slide, we said if we happen to know the assignments of points to clusters, we would be able to measure the cluster parameters, mu and sigma, via maximum likelihood estimation. On this side, I'm saying if we happen to know the parameters of each of the clusters, then we would be able to find out the assignment of those points to the clusters via the class likelihoods. Seems like we're running into a chicken and egg problem here. Yes, Shima.
So can you tell me what's the difference between soft clustering and mixture modeling? I know that mixture modeling is somehow generative, maybe, but
That's
the
a good
shape
question,
of
and
clusters.
that's a very good question, and I'll address this at the very end of lecture. But you're right that soft clustering is a special case of mixture model. I'll give you the exact relation at the end of lecture. Okay? Excellent. So what I'm saying is this, that we have somewhat of a chicken and egg problem in that if we knew which points came from which one of the sources, then we could estimate the parameters of those sources. And if we knew the parameters of the sources, then we could estimate which one of the points came from those sources. But we have to start somewhere, right? We don't know, need to know the parameters to guess the sources and need the sources to estimate the parameters. So what do? We have to start somewhere. What did we do in k-means? We randomly initialized our centroids and just started our iterative process from there. So the overview of the expectation maximization algorithm for Gaussian mixture models is as follows. We start off with randomly placed sources, just like we did for randomly initialized centroids. And then for each of the points, we're going to guess which distribution it came from. And then we're going to assign the points to those distributions. We're going to use those values to then update the parameters of the distributions, and then we iterate finally until convergence. What does this look like for the 1D case that we have? Let's say I'm in iteration 1. I've just randomly placed the sources based on some mean and some variance, and then I get the assignments in the colors on the plot. Based on those assignments, I'm going to update the parameters, the mean and the variance of each of the clusters, and then I'll do this a bunch of times until convergence. By the way, completely unrelated to this, but about the slides, Tix is a very powerful tool in LaTeX. It takes a lot of time, but if you're a fan of LaTeX and if you're a fan of creating slides that last a long time, all of this was done in Tix. Just I have a few white hairs because of it, but it turned out nice in the end. So it's effort that amortizes over time.